Hello, this is Jeremy, and in this video, I'm going to go through a couple of examples of using basic counting with theoretical probability. Now, these examples are very, very simple, and the reason that I want to show them to you is because these simple ideas apply even to more complicated probability questions. I mean, just look at part A. When flipping a coin, what's the probability of getting tails? I think you already know that that's 50%, but the question is, how does that work with the new ideas of sample space and everything else like that that you learn in a probability course? Well, think about it. When you flip a coin, what are all the possibilities? Well, heads or tails, right? So that's the sample space, S. So S is heads, tails. And so when I ask a simple question like, what's the probability of tails? And you go back to this idea of, well, as long as the events are equally likely or the outcomes are equally likely, then I can say, well, it's the number of ways the event can happen divided by the total of things that could happen. Well, that's actually the number of things in the event, which is just 1, out of the total number of things in the sample space, which is 2. So that's why we can say something as simple as, well, it's 1 out of 2. Really, what we're using is the same idea of else equally likely simple events and counting and sample spaces and all that, even with a simple problem like this. So when you get to something like B, we're going to use the same process. We're going to say, okay, if I'm talking about flipping 3 coins and I want to know the probability of something happening within that, the first thing I should really think about is the sample space. So when I flip 3 coins, what could happen? Well, you could get all heads, or you could get 1 tail, right? It could be the first one, it could be the second one, or it could be the third one. Or you might end up with 2 tails. Could be the first 2, could be the last 2, or maybe even the outer 2. And then finally, you could end up with all tails. The order doesn't matter how I think about them. I know that I should expect 8 things by the multiplication rule. So I have 1, 2, 3, 4, 5, 6, 7, 8, and that's the size of my sample space. So as long as I'm talking about an event out of this that has equally likely and it has equally like outcomes, then I can just go ahead and count. So I can say, okay, well, probability of getting tails exactly twice will be the number of these events that has tails twice. So that would be this one, and this one. So that's 3 out of the total number of things in the sample space. So that's out of 8. So again, same idea. Count what's in the sample space, count what's your event. Take a look at part D. So a committee is comprised of 8 men and 4 women. Find the probability that a woman is chosen if 1 person is selected from the committee. Now this one, I'm not sure if I really need to write everything out. If we're just going to randomly select from the committee, then we have everybody has the same chance of being chosen, so we have that idea of equally likely outcomes. And so how many people could be chosen? That's the size of the sample space. That's 12, right? How many of these people are women? That'd be 4. So this would be 1/3. So here it's a little different because the sample space is practically written out for me already. I didn't really have to write it out. I just had to think about what the total was. And then finally for part E, a very practical question. On a multiple choice question in an exam, for instance, with 4 answers, what's the probability of randomly guessing the correct answer? So if there's only 1 correct answer, which is what's implied here, then the number of ways you could guess the correct answer is 1 because you'd have to pick the right answer. And then how many possible answers could you pick? That's the sample space, so it's 1/4. So in other words, a 25% chance. So in all of these cases, I just had to consider the size of the event and the size of the sample space, and that's because we have equally likely simple events, also known as equally likely outcomes.